everybody. My name is Jakub Fojtl, and before I start, I would like to apologize in advance because this week I went through a horrible cold. In Czech Republic we call it rimička, and it sounds really nice and cuddly thing, but it's like madness. So my voice is not 100% okay, so I hope you will enjoy the talk anyway. So welcome to the talk itself, which with slightly provocative name, Infinispan in the world dominated by raft. Now, the title of the talk was based on the assumptions that once a developer who is working on an application outgrows a single relational-based database, they tend to pick raft-based distributed databases because they tend to offer very similar properties to how relational databases works. With that said, just a little bit background of myself. I work in Vysoft on a flagship product called SafeQ, and SafeQ is an enterprise workflow system. Don't get me going into it. For those of you who knows us, it mostly means we are writing software for printers which look like this. And this kind of sounds boring. However, for me, the really cool thing is that the SafeQ product actually is a highly available distributed system that runs outside of our control. We are not doing cloud-based deployments. We are doing on-site deployments, which is kind of a lost art, I think, because all the DevOps movements and site reliability engineering kind of not focus on that very much. So we need to do a lot of things on our own today. This brings me to the agenda of the talk. Since Infinispan is helping us really a lot to build a distributed system on foreign infrastructure, I will briefly talk about it. I will do like a 5-minute, 10-minute crash course of Infinispan. But the core of the talk is really how we are using it. I will show you some tips and tricks about how we are using the Infinispan, and then I'm going to show it to you in a real code, in a sample application. So Infinispan. The tagline of Infinispan is, it's a distributed in-memory data grid. Now, the distributed is fairly simple. Infinispan is a distributed system, or can be distributed system. The in-memory means that the data you put into Infinispan by default runs in the memory, not on the disk, it's not persistent. However, you can configure it to be persistent. And the data grid, it's the most interesting part. The data grid means, what the authors meant by the data grid is that Infinispan doesn't have a master-slave or leader-follower architecture. It has more a peer-to-peer approach where every node in the cluster is equal to another. It has 4 main use cases, where the first one is a distributed cache. You can use Infinispan you can put Infinispan between your application and your database to quick things up. And if you have an application that runs on multiple nodes, then the Infinispan can be a distributed cache. The second use case is a NoSQL database, and that's the use case I'm going to be focusing on today. The third use case is event broker, similar to Kafka, for example, and then you can use Infinispan for data analytics. When you want to work with Infinispan, you have 2 kinds of options. If you write a JVM application, you can load Infinispan in your process, and then talk to the Infinispan directly, or you can use some of the server distributions of the Infinispan. Infinispan, since it's a project from JBoss of Red Hat, the server distribution uses Wildfly application server, or rather application server libraries, I would say today, and you can even run it in Docker and etc. If you run Infinispan in your own process, you can work with the Infinispan directly with the Java API. There is no remote calls between you and the Infinispan, and it's really nice, most powerful API. However, if you are not, There is one native client for Infinispan, which is called Hot Rod. You can think of it as a database driver, which was written for the purpose of talking to Infinispan. Then it has a few more ways how you can interact with the Infinispan. However, I would not recommend you using them. REST over HTTP is, for example, one of them, but the API exposed via REST today is really minimal. So just you can start with it and slowly move to Hot Rod. What are the building blocks of Infinispan? So one of the fundamental building blocks of Infinispan is JGroups. JGroups is used to handle the cluster membership and the communication among the cluster. It's also another project from JBoss project. Then it uses Lucene if you want to perform indexes, because Infinispan is a NoSQL data store. It does not understand the value. If you need to, for example, search by something that is in the value, you need an indexing system, and you can use Lucene for that. Then it uses JBoss marshalling. If you put something to the Infinispan and you know that the Infinispan will need to send it across the cluster, you need to serialize it somehow. Infinispan by default uses not the native Java serialization, but rather the JBoss marshalling. If you consume Infinispan from another platform than JVM, yes, it's possible, then you can use proto-buffers to do the same job that JBoss marshalling is doing. Infinispan supports push events, so unlike with the traditional database, where when you want to obtain a data from the database, you need to explicitly put a query to the database and the database will respond, you can attach listeners to events of the database, and the database will then give you real-time events based on inserts from some other client, and you can use it for building really pretty reactive applications. Last block I want to mention here is that Infinispan supports transactions. It uses the transaction manager, or rather one of the implementations of transaction manager. The Infinispan can work with almost any implementation, and it has 3 built-in transaction managers based on the use cases you need to achieve. But what's nice about Infinispan is that Infinispan is really modular, and you can only use, only load what you are really using. So JGroups is something that will be always there. That's something that cannot be changed. However, everything else, it depends on you whether you want it or not. You can include it, and you don't have to. Since Infinispan works with data, let's get to how Infinispan works with the data. So Infinispan has 4 modes of data distribution. The first one is a local mode, where Infinispan is not really a distributed system. You can simply load the Infinispan, store the data there, fetch it later. The Infinispan doesn't talk with anybody. The second mode is called the invalidation mode. With the invalidation mode, you can think of it as if you have more applications talking to the same data store, and one application changes something in the data store, you can use Infinispan to send invalidation messages to other applications that talks to the same data store. And basically tell them, I changed this kind of data, please obtain the new one from the database. In this scenario, the Infinispan actually doesn't hold any data. Now it's starting to get interesting. Replicated mode is a distributed system, and Infinispan holds the data. In the replicated mode, when you put something to one node of Infinispan cluster, the information is stored to every node in the cluster. And then the most interesting one is a distributed mode. And I'm going to talk more about that. In order to explain how distributed mode works, I need an Infinispan cluster and a client that wants to write some operation to that cluster. During that write operation, the Infinispan will try to run a function on the key that you want to store into Infinispan, and the result of that function are primary and secondary owner of the data. This function is called consistent hashing function. The value along with the key is then only stored on those green nodes, which have been selected by the consistent hashing function. The number of nodes where each data will be stored can be configured per cache, and it's called the num owners. And this basically means that the write operation requires fixed number of nodes, no matter how large the Infinispan cluster is. This basically means that the Infinispan scales linearly the write operations to pretty big sizes of the cluster. It has synchronous and asynchronous versions of the write operations, where the asynchronous version will wait for just one node to accept the write, and the synchronous version will write to all nodes that are supposed to acknowledge the write operation. And the Infinispan by default will always accept your write operation as long as there is at least one node that is working. So the Infinispan is really an AP system where it will always choose availability over consistency and have embedded mechanisms how to deal with partitioning. Now, since I mentioned raft in the title, let's compare how raft deals with write operations, or rather raft-based databases. And in order to explain that, I need a raft cluster and a raft client, and a client that uses this raft cluster. Let's perform the same kind of operation. Now, in this case, at the time when the client tries to perform the write operation, there is already one leader that was elected before, and the leader election is like another very complicated thing. I could do a talk just about the leader election, and I'm not going to do that. And the leader is responsible in the raft cluster to distribute the write operation to every node in the raft cluster. In another way, the leader is responsible for keeping single, partially ordered, replicated log. So every operation, the leader is there to take every operation that the client tries to perform on the leader and guarantee serializability on the requests that matter. The raft cluster will accept write operations as long as there is at least more than half of the nodes in a healthy state. So you can think of raft as a CP system where it will prefer the consistency over availability. If the system cannot guarantee you the consistency, it will simply shut down. So the raft cluster will be available as long as more than half of the nodes is healthy, which means it works best with the odd number of nodes. The raft databases also tend to have a complicated recovery. When you get into the state where your cluster is not responding, all you can do is basically recreate the cluster again, because adding and removing cluster is also a write operation, and that is not allowed in the state when the cluster is unhealthy. So I don't think it's fair to compare raft with Infinispan or consistent hashing functions. I think that raft is really great in use cases where what you really want is to scale your read operations, where you have many more read operations than write operations. And if you want to know more about how raft work, I really recommend going to secretlifeofdata.com, which has nice visualizations showing all the aspects of the raft protocol. Now the more interesting part, how we are using the Infinispan. So let's imagine that you have an Infinispan cluster at your customer that you are using to run your application. And basically you need to count with the fact that there will be a split, that the split will happen. It's not a question of if, it's rather a question of when. By split, I mean that there will be some magic sort that will create basically from your one cluster two other clusters. The first thing to note about that is that in this case, the Infinispan will start a rebalancing process. The rebalancing process basically means that when you had one cluster, it could happen that on, let's say, for example, this node, you could have a value which is like a primary owner, and the secondary owner could be here. So now you are in the situation where on both sides of the cluster, you have only one replica of the data, but the Infinispan is configured to have two. So what it will do is that it will try to ensure that in both sides of the clusters, there are at least num owners number of replicas. What is also happening here is that you can also have keys, or rather data, which are stored here and here, and it means that the data is not available in this kind of cluster, and you need to work with that. However, since Infinispan prefers availability over consistency, both clusters are available. And if both clusters are available, there will be clients that will talk to the cluster. And since they are talking to the cluster, they will perform write operations. And then, when the problem is solved, you will end up with accumulated data on both sides of the split brain, on both sides, like in both Infinispan clusters. And sorry, every consistent hashing function-based database needs to have an embedded processes which are named in general conflict resolution. Conflict resolution are methods that will help you to deal with the merging of the accumulated data on both sides of the cluster. Infinispan calls that a merging. Now, the merging is fairly simple if you are doing changes to, when you, for example, create a new value on one side and totally new value on another side, there will be no conflict because the first one will work on key 1, the second will work on key 2, and you can simply merge them together with no problem. However, the problem happens when one client changed the value of one key on one side of the cluster, and another client also changed the same value under the same key. At this time, the Infinispan needs to decide how to merge them together. Now, it has some automatic policies embedded. However, I think they are useless, and it's not Infinispan's fault. It has 3 automatic merging strategies. The first one is always prefer the original primary owner. The second one, always prefer the value that is non-null. And the third option, which I quite like, is to remove both of the changes if there are any. However, usually, why Infinispan cannot offer like a sensible policy? It's basically because it's your application, it's your business logic that needs to decide how to merge those operations. And Infinispan can't do this decision for you. So it also have a manual kind of mode where you need to merge those operations together. By manual, I mean implementing an interface which is used for merging, not manual in a sense that administrator needs to go there and do some changes to the database itself. And when you are doing that, you basically need to decide what happened first. And that brings me to a question of time. We as people tend to perceive time as something linear, as something which is a property of when I have an event that happened at a T1 and an event that happened at a T2, I can always say that the T1 happened before if it's on the more left side of the time. I can use time to measure the distance between the events. However, that's not how the implementation of time works in today's computers. Time in today's computers is not continuous. You can have an NTP client running on your computer that will decide, oh, you drifted 5 seconds into the future, let me correct that, and we'll put the server to 5 seconds back. And also, it's very hard to synchronize clocks across the cluster. Now, Google tries to do something about it with its own product called Google Spanner. It's another database. And what they are doing is that they are creating something they call true time, and they use a special hardware based on the GPS that will try to ensure that the time on the computer has those kind of properties. But unless you are Google, do not ever use time for coordination. Do not use time for ordering. Now you might argue that, of course, everybody knows that this slide shouldn't be here in 2017, and I would tend to agree. However, always when I'm part of the discussion about ordering in distributed system, there is always at least one guy that proposed timestamps for that. So that's why I put the slide there. So you cannot use physical time. You can use for ordering like logical time and many implementations of that, for example, vector clocks and others. There is a really nice talk that I saw recently on InfoQ by Kavya, which happens to be just about that, but it's not the approach that we are doing. What we are doing is that we have something what I would call append-only approach. In the append-only approach, we only add data to the database. We are not modifying the database. So once we store something into the database, we do not change that. We model changes of the data as events on that entity. It's not really event sourcing, where the event sourcing is used as your primary store of the data. It's rather, if you want to change one entity, we only change it by creating an event on that entity. And we have 3 kinds of events in our system, where the first one is where the order of the event is determined based on the type of the event. What does it mean? I'm really terrible at thinking about examples. One of the examples I came to is airplane journey. And with the airplane journey, you can have 3 events, for example, takeoff, landing, and taxi. And the taxiing cannot happen before the landing. The airplane needs to land before it can taxi. So if you happen to receive events taxi landing, you always know that you need to order that in order takeoff, landing, and taxi. The second kind of event are commutative and idempotent events. It basically means that if I have event 1, if I have entity and I apply event 1 on it and then event 2, it will have the same effect as if I apply event 2 and then the E1. By idempotent, I mean that if I apply E2 many times, more than once, it will not affect the result of the applying that event to my original entity. I would like to say that those properties are kind of inspired by CRDTs, but this is really just a 3rd grade math. So the third kind of events that we have is where order does not even matter. For example, delete operation, it does not really matter when the delete operation happened, because after that you cannot do any more events on the entity. The result of such data approach is that out-of-right operations do not require coordination at all. What I mean by that and why it's good. Let's compare it with the operation that does require coordination. For example, the sequence number generation. The sequence number generation is, for example, used in your relational databases for your primary keys, where you need to go from one to another number, and the number is generated on your database. If I want to achieve a sequence number generation, and if I want to implement it properly, I need to use some kind of coordination mechanism. For example, two-phase protocol. So let's say I have a client which thinks that the state of the sequence is 4, and it wants to progress to 5. What it needs to do with the two-phase commit is that it first needs to ask and say, okay, prepare everybody, can I jump to number 5? Then if everything is okay, all the nodes in the distributed system will tell you, okay, you can do that. There is no other client that did it before, so you can do that. And then the client can say, okay, I'm jumping to number 5. And again, if everything is okay, the cluster will respond, okay, I accepted the changes, and the client is now on the number 5. Now, in order to do that, I generated like 3, 6, 12 messages, and I didn't go into error cases. Let's say that there was another client that tried to go to the same to the number 5. This communication would get really messy real quick. It would generate many more messages just to progress to this number 5. Whereas with the write operation or any operation that don't require coordination, you can simply store the write operation without direct involvement of other nodes. No messages, no problem. And the write operations brings me to transactions. You have two kind of use cases for transactions, where the first one is, I want to perform the transactions for the order of operations, and I already showed that we don't need that. And the second use case for that is, I either want to write everything or nothing, because otherwise I would end up in the damaged state with the damaged data. That basically means that if I want to perform a write operation, and in today's APIs, for example, one post request in the REST-based APIs, it usually ends up being more than one write on the database layer, on the data layer. So let's imagine that I have one API call that will generate 4 calls to the database, and I want either all happen or none. Then I would wrap that into the transaction. However, we are not updating any existing data. We aren't using foreign keys because we are in a NoSQL world. There is no schema, so the database will not punish me for not being, I can't find the word, consistent. What Infinispan can do for me is that I can reference to an ID that's not in the database yet. And this basically means that the data cannot be damaged. So we are not using transactions as well, because transactions brings another complexity of the coordination, and we don't want to do that. However, that comes with a price on the other side, on the query side, on the read side, because the read query must be designed to handle the missing parts. It can happen that one write will like succeed in only writing 2 out of 4 operations, and then the query part must handle that somehow, either throwing away the incomplete parts or try to recreate them based on the use case in your application. Another disadvantage of this approach is that it will leave unwanted artifacts in the database, meaning that those 2 writes out of 4 are really there for nothing unless I get to the additional 2. So that may create a clutter in my application. Now, it's not a problem for us, since we are keeping only really fresh data, like a month old, for the user in the NoSQL store of Infinispan, and we clean everything that's older than that. So that's not a problem for us, but can be for you. This brings me to the client, as you will see. Now, before I do that, this is kind of a standard architecture that you will end up with once you start using Infinispan. So you will have some kind of client software, be it single-page application or some other. And then you will have Infinispan cluster, and the client will not talk to the Infinispan cluster directly, but rather through services, microservices. And in this kind of scenario, what we are doing on the on-site deployment side is that we held the client responsible for finishing the user's wishes. What does it mean? It basically means that if the user wants to work with your software, it will usually generate some requests, some operations to the server side, to your microservice. So let's imagine that this will create a request on a REST API of the microservice. Then after some magic in the microservice, it will generate those 4 writes that needs to be stored in the Infinispan cluster. And during that, the microservice fail. What can happen is that the client, of course, will observe something like HTTP 500. And in the Infinispan cluster, the microservice might happen to write those 2 writes out of 4. Now, in this case, what I mean by the client responsible for finishing users' wishes is that our client needs to perform a failover, and it simply will try to find another healthy instance of the type of the microservice that it usually talks to. So it will simply retry the same kind of operation on that microservice, and that microservice should generate the same kind of 4 writes to the Infinispan cluster. So this will basically add the 2 missing pieces to the database. Now, this is partially possible because we use UUIDs for keys, and the UUID for keys gives us nice property that the key can be generated on the client application directly. So you know that when there was, for example, post on another to create a new kind of entity, part of the message will be an ID that happen to be the ID in the Infinispan. So that's why this will create very the same 4 kind of write operations. We do this because it's very hard to, in the traditional cloud-based environment, you would put a load balancer between your client and the microservices, and the load balancer would do this job for you. However, it's very hard to bring and install and mainly take care of the load balancer at the site of the customer. So that's why we are doing application level failover. Users nowadays are expected that when some server that the user never happened to see fails, it doesn't matter. It's still, the application still should do the right thing, because that's what the cloud-based application thought this user. However, when the client is down, the user usually has no expectation of client finishing the user's wishes. But as I heard in the keynote by Todd Montgomery, I think users think of software crap in general, so it shouldn't really matter. Speaking of UIDs, we are not using them just for the, let's say, primary keys. We are also using them to recognize the requests from themselves. Basically, we will do, with each request, we will put there something like operation ID, and this can be used to achieve 2 things. The first of all, just doing that will make your request idempotent. But you can use it on the application level to distinguish between the retries and between the 2 wishes of the user. So this will distinguish between whether the user wanted to perform the same operation twice and when the client decided to create a retry. So the retry should always preserve this operation ID, while the new kind of operations should generate a new UUID. And this is also great for monitoring. Now, that would be all to how we are using the Infinispan, and I see that I have 15 minutes, so I can jump to the demo. In order for the demo to show, I need to go to my IDEA. Now, I usually use IDEA in the black mode, in the Darkula theme, but it's kind of not visible, so I hope that I will be able to work with that. And what I want to show you is really simple application where I have a client that will be talking to a job service, since we are a company that are basically working with print jobs. So I kind of, as I said earlier, I'm kind of bad with coming up with examples. So I will use that. And I will host Infinispan in my process. So I will do the in-process hosting. That's why I will be using the Infinispan API directly. I will run the Infinispan in the distributed mode, as I was explaining. So that's why I'm creating 3 kind of nodes with num owners set to 2, so that we can see how Infinispan works with that. Now, in this kind of application, I implemented 3 use cases. However, I will show only 2 of them. The first one, when the client will send jobs to the job service, and then it will try to obtain the list of jobs from the job service. So let's go into that. I created a Spring controller. Where I basically talk directly to the Infinispan. I'm not creating layers that would prevent from showing what I really want to show. And this controller have a method that's called accept. Let me go here, and the accept basically is something like this. So when I send a post request to this URL, it will create a new job. In the request, there will be an instance of the job ticket, and my service will either respond with 201 HTTP status code on success, or 500 if anything else goes wrong. This is really a toy example, so I'm not dealing with authentication and all other stuff. What I will then do is that I will try to fetch the job list of the user. For that, I have another resource in the API. It's just simply get operation on users, basically the same kind of URL. And when I do that, it will return a list of job tickets that I previously stored there to show my jobs. Okay, so the job ticket is how I represent my data on the API level. It's not how I represent the data in the Infinispan. So I need to convert that from like the job ticket to the way how I store the job ticket. And I store job ticket by separating it into 2 classes. One is job, where basically job represents an identity of a single print job. And by that, it will store its ID that is generated on the client, the owner of the job, meaning the user who sent the job to the job service, and then some kind of job title. Along with that, it will create a job detail 2D, because I anticipate that we will have also the 3D job detail, so that's why I separated it. And the job detail will also have the job ID, but then like 2D print things, so like things like number of pages, how many, if it's a color or a black and white print job, and if I want to print the job on both sides of the paper or just on one side. And the approach where we use Infinispan so that we can first, where we do not use transactions, you can clearly see that I'm not using transactions, otherwise this code would be much more complicated. I simply take the job cache of Infinispan, which I can get this way. Let me go to Infinispan configuration. So this is XML, which represents a configuration of the Infinispan. And here I'm saying, okay, I want to create those 3 caches in the distributed mode. And here I'm saying I want to store it on disk. I don't want to run it in memory because with the NoSQL scenario, I'd rather store it to the disk so that I have less complicated recovery in case of failure. So I have three kinds of caches that I can use to store data and obtain from. And that's what I'm basically doing here. So the Spring will inject default cache manager, which is like a gateway to Infinispan caches. And then I can use the get cache, name of the cache that I put in the XML to obtain that. Since that moment, I can work with the cache directly here. So the method put if absent will simply store this value if it was not there. If it was there, it will do nothing. And since we are working in a way that we never change what was stored to the database, I don't need to take care, I don't need to handle the case when I expect that this job is something different than what is stored there right now. Since I want to show something, I put a code between another write to the cache. I want to store the job detail to job details cache, and this works in kind of a similar way. And since I want to represent how the query side will deal with incomplete write, with this if statement, I want to create a scenario where the job service failed during the write operation. So I will write 3 nodes of my application, and if I send a request to node 0, basically I will never be able to complete the request, and that is good for demo purposes. Then I have the get operation, which should bring me the job list. And here I basically need to worry about the artifacts that are not complete, where I only store the job, but not the job detail. And that's basically what this method is all about. So first of all, I will use Lucene to obtain all the jobs based on the property owner. And then I will iterate over every job that was written to me and will obtain the job detail. Then I will merge the job and job detail into job ticket, store it into my collection, and then at the end, return that to the user. So in order to show you that this works, I will run all 3 nodes. This should take a second. I'm sorry. Okay, first one, node 0, that's the faulty one. Node 1, that should be healthy one. And finally, node 2, okay. Now I should wait for the Infinispans to discover each other. JGroups is used for that. I run Infinispan on the local host, and I can do that by running the Infinispan on different ports from each other. So I will have a node 1, which will run on the port 7800. The API, the REST API will be available on port 8000. The node 1, Infinispan will run on 7801. The API will be available on 8001. And finally, node 2, you get the idea. Now, because of my illness, I couldn't finish the client, so I basically will show you how it works with the generic REST client, the Insomnia one. And in order to show you how it works, I created this URL, and I will perform a get operation to show that I now should not have any job in the Infinispan. Yes, I have no job in the Infinispan, so it returns nothing. And now let's post to the unhealthy node some job. So The job ticket in the JSON world will look something like this. I also generated a UUID beforehand. What I quite like, that's something that Amazon showed us, is that I'm not using the type UUID directly. I use it as a string, and I will append the kind of operation or the kind of the place where I want to use the UUID. So here I will have job.UUID. When I see that, I immediately can know that this is a primary key of a job. Now when I run that, and I have a breakpoint here because you never know. Now this should be fine, and now this should not. Okay. The client will see 500 internal error, and in this case, now I have incomplete data in the database. I have there just the job, not the job detail. So if I get the jobs now, since I decided that I will throw away all the incomplete things, the job service should return also like an empty array. Now this job, now let's call the post resource on another node, for example on the node node 2. When I now hit send, I will also get here, but now the if will be skipped and everything should be stored okay, and it is. It returned 200 created. So now when I get all the jobs, I will get the job that I send there. So that is for the demo. Takeaways. What I'd like you to take from this talk. Well, first of all, I don't think that raft is bad. Raft is not bad. It's just that I saw it used in use cases where I think some other methods would be a better fit. Second takeaway that you can do with any application is that if you are building the distributed system, try to think of it in a way that you will avoid coordination at every time. Coordination is bad. It's not only slow, but it will put you in danger when something bad happens. Distributed system is kind of hard to encapsulate. You need to basically be aware that you are building a distributed system from the end-user facing client all the way down to the database. Now, two general takeaways. The more resilient your application is, the easier your life will be once in production. And know the properties and limitations of the building blocks you use. Thank you very much for your attention. Any questions? Do we have time for questions? Cool.
I've noticed that you did a query with Infinispan cache.
Yes.
What kind of querying language is available, or
that's the Lucene indexing. It uses Lucene and Hibernate search.
Other questions? If not, thank you all.
Thank you very much.